Hello. In this segment, we're going to be talking about CPU performance enhancements. Already we've talked about the use of RISC-based techniques, and these would be applicable in this situation as well in general. Fewer instruction formats that are fixed length means that we're going to have faster instruction decoding. More general purpose registers means that we're going to use fewer memory accesses. But beyond these two general performance improvements, how can we improve the performance of our processors? To do this, we have to look at the clock cycle and the instruction cycle. Most instructions are going to take several clock cycles to execute. There are 5 stages to executing every instruction in general in a RISC machine. You're going to fetch the instruction, decode the instruction, execute the instruction, access memory for a load store if need be, and then write back to memory, or write back to the registers. Each instruction is going to take, each stage of this is going to take 1 clock cycle, so a complete instruction execution takes 5 clock cycles. The question is, can we do better than this? To do this, let's kind of compare the execution of instruction to building something in the real world. The question is executing an instruction more like building a building where I have to start and then continue on to the next stage and the next stage and the next stage because each building that I build is going to be unique? Or is each instruction more like building a car on an assembly line, where each stage does something a little bit different to the instruction that's being executed? The 5 stages of instruction execution are pictured here. Notice that, say we're using an add instruction. The ALU that's being used in stage 3 is idle in stages 1, 2, 4, and 5 because the add only takes place in stage 3 and that's the only time the ALU is used. If we could have the ALU executing another instruction at a different stage while these other ones are executing, then we can overlap and reuse the hardware that we already have. The solution then is to offset and overlap in a pipeline. So, the first instruction is fetched. While the first instruction is being decoded, we fetch another instruction from memory. While the first instruction is being executed, we're decoding the second instruction and then fetching the third instruction. While the first instruction is accessing memory, we're executing the second instruction, decoding the third instruction, and fetching the fourth instruction. And then by the 5th cycle, we are having the complete use of all of the functional units inside of our CPU executing on 5 different instructions at once. So, at this stage, once we've filled the pipeline, every cycle we complete the execution of 1 instruction. And so a 5-stage pipeline executes 5 times faster than a single stage of execution, where each instruction takes 5 discrete cycles. There are some problems that we have with pipelining, and these are data dependencies and structural dependencies. For data dependencies, also known as register interlock, if we have an instruction, the second instruction, that depends on the result that's calculated in the first instruction, then we're not going to have the result available in time for the execution. Let me show you a picture. It's not until stage 5 for the first instruction that we have the result. If that result is written back to the register file but is needed by the second instruction, we need it in stage 4 for the other instruction. We need to move it back in time, but we can't move it back in time. So there's 3 solutions that we have to this. The first solution is we forward the result independently from stage 3 of the first instruction to stage 3 of the second instruction. That's one way. The other way is to stall the second instruction for 2 cycles. Now this underutilizes our hardware and so is not very efficient, but it is a simple way to do this. The other thing that we could do is reorder the instructions so that we eliminate the dependency. Maybe we can insert 2 more instructions between these so that the result is available at the right time. Now that's difficult for a human. Compilers can do a little bit better at it, but we would still have to have one of the 2 other solutions, either stalls or forwarding, in order to completely solve the problem. There are also problems with structural dependencies. This is for branching. When the first instruction determines that a branch is going to be taken, then the next 2 instructions have already entered the pipeline, but they shouldn't be there because we're not executing in sequence. We're going to jump to a new location for execution in memory. So let me show you a picture of that. If the first instruction reaches stage 3, the execute phase, and we determine that we're going to branch, the other two instructions have already entered the pipeline. They're already in flight, as we would say. So how do we fix this problem? Well, the solution is to predict that the branch is not taken. In other words, we would assume that we're not going to take the branch that the next two instructions should complete. If they shouldn't, because the branch is taken, in other words, if we've predicted wrong, then we need to cancel those instructions in the pipeline. Now, this is equivalent to inserting stalls, but getting the right answer slowly is better than getting the wrong answer fast. So risk in pipelining lets us use each functional unit to its most effective use. But what if we had multiple functional units? What if we had multiple ALUs or multiple decoders? If that's the case, then we could actually be simultaneously executing stage 1 on multiple instructions. In order to do this, we need to be able to get multiple instructions at once from memory, so we need to have a very large path to memory. So this is typical scalar processing. This is what we saw previously, the standard instruction pipeline. And at the end of every cycle, we are completing the execution of one instruction. So one cycle, one instruction, so 1-to-1 ratio, that's called scalar processing. One copy of each functional unit utilized fully. In superscalar processing, though, we have more than one copy of each functional unit. Effectively, what we have is multiple pipelines at a time. So in this particular picture, we have two pipelines that are executing the instructions. So we can simultaneously decode and simultaneously execute. And while that execution is happening, two other instructions are being simultaneously decoded. Okay? There are problems with superscalar processing, and these are the same general categories that we had with pipelining. So these are data dependencies and branch dependencies. Except now the problem is that forwards or stalls or canceling of instructions need to take place on multiple functional units in several pipelines at once. So one pipeline could be executing an instruction that's a branch. We might have to cancel an instruction in the second pipeline. And so CPUs become very complex again, but yet it's not uncommon to have 2 or even 4 separate execution pipelines in modern processors within a single core. So in summary, RISC-based CPUs are going to offer some general performance enhancements due to simplified formats and single clock execution. Pipelining, though, is going to allow multiple instructions to be in various stages of execution at once. At the end of a single clock cycle, then, we will be completing one instruction once the pipeline is filled. Superscalar processing duplicates the pipelines in a single core to have multiple instructions executing simultaneously. But this involves duplicating the functional units within the CPU, which adds complexity and cost. Data dependencies and branches are hazards that we have to deal with in both pipelining and superscalar architectures.